This is the second of our talks, having a look at how data gets to be stored within memory. This one we're going to have a look at the notions of duration, of scope, a little bit more about how visible and how accessible and how long-lived data is within memory. Sort of having a look then, or just in the notions of duration and scope. Hopefully you remember from the last talk when we had a look at how memory is partitioned generally within an executable program. There was one of three different areas that we could store our data. It might be stored as part of our static storage. It might be stored on the heap in terms of dynamic storage, or it could also be stored on the stack in terms of automatic storage. And these three different regions or areas, they say, or cater to different needs or the storage of different types of data. And this gets into the idea or the notion that when we create data, well, some data we want to hang about to persist. In other cases, we're just simply creating data to use it for some quick purpose and then discarding it. And those different requirements in terms of how accessible, how long-lived the data is, they lend themselves to different, if you like, allocation management techniques, which in turn lend themselves then to being stored in different parts of memory. When we're trying to better understand the need for these three different areas, there's a few concepts that come in that are quite useful by way of how we think about our data. And they're the notions of scope and of linkage. So by scope, what we mean here is that we are defining just how visible this piece of data is. That it is global scope. That means that, when I'm talking about scope here, we're talking about scope within an individual file as opposed to across multiple files. That's more into linkage. But scope here is talking about an individual file. So something that's global within a file means that we've declared it once, and then after the point of declaration, or definition rather, it is accessible anywhere from any method or from any particular point. If it has local scope, it means that it is only visible within the generally the function or the block of code within which it has been declared. And whenever that block of code exits or terminates, then it's not visible anymore. Linkage, if you think back to C++, each file is compiled individually. So linkage gets into the notion of just how visible something is in other files. So if something has external linkage in C++, it means that it is, for example, a piece of data that may be defined in one file, but is visible or accessible from another file. In turn, something with internal linkage is a piece of data that is only accessible and visible within the file within which it is defined. So we're going to break these down into a little bit more detail and look at some of the aspects of how they're supported within C++. We'll start off looking at automatic variables, first of all. So things like parameters we're passing into functions, just ordinary variables that we declare. So you can see an example down here. We've got a function or method called foo. A is one of the parameters that's passed in. So again, that's an automatic variable. It's something that will get to be stored on the stack. They automatically come into existence, and they automatically expire, if you like, whenever the block of code terminates. In this case, whenever the foo method completes. Line 3, we're declaring a local variable, and b is equal to 4. So again, we simply just declare it. It is automatically created for us, and then that memory is automatically released or freed up whenever b goes out of scope. So automatic variables, they have local scope. They are only declared within the block in which they're defined. They have no linkage. They're not, they have internal linkage. They're only visible within that defined function, not visible from any other file. A little bit of the bottom, I mean, automatic variables, you can initialize in any expression that can be evaluated when the declaration is free, so you can initialize them any old way you want to. Just a little bit more about the notion of a block of code. In most cases, we generally think about this as a function or a method call, and it's declared within that, or after the point of definition within that. Strictly speaking, a block of code is something enclosed between braces. And we have an example shown here where we actually have two blocks of code. So we have an inner block within our method. And this applies to if-elses. So each, the if and the else will have their own respective blocks that get to be executed. So within this chunk of code, we have two local variables, a val and b val. And whenever we call the method, at that point we allocate, reserve a piece of memory for holding a val. And whenever we have introduced it within the code or defined it, it's then accessible, it's in scope, we can access and we can manipulate it. Line 4, we're starting a new block of code. And at that point we allocate or set aside whatever space bval needs to have. Whenever we introduce that or define it, then it's available, it's in scope, we can use it. And line 8, the block of code finishes. So this particular point then, bval actually expires. It's out of scope, it can't be accessed anymore, and will free up or release the chunk of memory that notionally or we had reserved for it to be used. And a line, in this case line 10, whenever we reach the bottom of foo, then a val goes out of scope, can't access it anymore, and we also free up the bit of memory that we had originally allocated to it. For automatic variable management, so this is the types of things that we create them and then we discard them, and generally they're short-lived. We do this very, very often. So we need to have some mechanism that enables us to very easily allocate memory and very easily free up memory. This has to be a low-cost and very quick, very efficient way of managing this memory. Probably the best way of doing it is actually using a stack. So anytime we call a method, we can simply push, if you like, a couple of integer-sized chunks, or reserve a couple of integer-sized chunks by pushing it onto the stack. And whenever they go out of scope, we can then simply pop those off the stack. So it lends itself to this type of sort of recursive, you drill down in, and then you're going back out, you release the memory. So that's where the stack gets its name from. It is the technique whereby you can very quickly allocate, reserve some memory, and very quickly free up that memory. There's a stack pointer, and by changing that stack pointer, we know whereabouts the free memory is and where it commences from. It is an aside. Most processors will have register variables on the actual processor themselves, and in for example C, you can actually request that some data is stored not in memory but actually stored on the processor, accessible within the processor itself, by way of getting maximum performance. There is a register keyword available within C++. C++11 though sort of moves away from that. It generally is up to the compiler or other processes to decide which data is likely to be accessed most frequently, and hence then should be sort of stored as close to the CPU as possible. For static variables, for static data, so these are variables that they exist for the complete duration of the program, so they always exist. So this is the first chunk of memory that we had after our program's data, the executable code. So things that whenever we run the program, commence it at the start, we automatically allocate these. They always exist. For static data, there is actually three different types, and they differ in terms of the form of linkage that they have available. So something that is externally linked, has external linkage, it means it's a static piece of data, is visible obviously within its declaring file, but also within other files too. For static data that has internal linkage, then, okay, it always exists, but it is only accessible within the file in which it is defined. And you can also have static data that has no linkage, that it is only accessible, so it always exists, but it is only accessible, you only get access to it within the block of code, similar to like an automatic variable, within the block of code in which it is defined. We're going to have a look at all three of these. For static variables, because they always exist, you can be zero initialized, or you can have a constant expression, something that whenever the program initially runs, you can give it that defined value, that starting value. We'll start off having a look at, if you like, well, what is the most common, or what's the most simple way of declaring a global variable. Now, you can see an example piece of code down here. In line 1, we're saying some global is equal to 3. It's not declared within a method, it's just declared standing on its own. So that is how in C++ you declare a global variable. It's something that is defined. It's static, it always exists in this particular sense. It has external, in this particular case we're declaring it in this way. It has external scope. So something declared in this manner is externally visible. It is visible within the file, but also potentially then visible within other files too. We're going to compare this then with the other forms where we may want to restrict its visibility just to this particular file. But this is our starter. Important to this, C++ is what's known as the one definition rule, and that states there can be one and only one definition of a variable. That potentially can introduce in some problems is the wrong word, but something that needs to be resolved. So in C++, as mentioned here, one definition rule, we're only allowed to define a variable once. Also in C++, when we're compiling each file, we compile it as a standalone file. So that if I have an external variable, something that is defined in another file, but I want to access it within a different compiled file, I have to have some way of indicating or denoting that it exists, it's defined in another one, I'm simply declaring or identifying it within this particular one. And there's a special keyword within C++ known as extern. Extern gives you what's known as referencing declaration, that I can have an extern integer. So I'm saying that it exists, but it is defined within some other file, not in this particular one there. I simply include it in this file. It means then I'm able to declare that yes, it does exist. I can then use it from this point. So it doesn't actually give you any new storage being allocated. For extern, you can see an example here of where it comes in. So we've got three CPP files, lib01, file01, file02. So in lib01 on line 2, we declare an integer a. And as defined as such, it's an external variable definition. It's not declared within a method. It's not a function parameter. It's just in its own. Hence, it's an external variable. And that's how it will be considered. Let's say you look at file01. If I want to get access to a, I want to use a, I have to use the extern int a. So there I am saying it's a referencing declaration. I'm identifying that there is an integer called a. It's notionally a global one. It's actually created or defined in some other file. In line 3, we're doing int b is equal to 2. So again, we're also not only declaring that there is an integer, we're also giving it a particular value. So again, it's similar to line 2. It's external variable. And in file01, again, if we want to access it, we do it in the same way. That's reasonably okay, reasonably simple. Line 4 complicates things slightly. This is lib01, line 4 of that. Here we have extern int c is equal to 3. Now, there's two things at play here. We've got the extern keyword. It is suggesting, or just after saying, that if you use extern, it means you are as a referencing declaration to something else in another file. However, you're also doing int c is equal to 3. So you are defining you're defining the value of c. So this is a bit of a mixed line, but it is actually permitted within the language. In this particular case, the definition of c being equal to 3 takes precedence, and the compiler is going to say that, okay, you've given c a value, so I'm assuming that you actually are defining it. You're defining what value it has. So line 4 of lib01 is also considered to be a variable definition. And in file 02, if we wanted to access it, again we do extern int c. So it's slightly confusing, but that's just the rules of the language. Example there about if we, this is where the static keyword comes in. So file 01, we're declaring external variable int called var, value of 100. And file 02, let's say I've written file 02, and I also declare int var is equal to 100. Now, it's also an external variable. If the compiler were looking at this, it's going to end up going, hold on, there's conflict here. So what we need to do, and this is where the static keyword comes in, if we want to declare a static, is always existing, but it only has internal linkage, it is only visible within the file in which it is, if you like, defined, then we use the static keyword. So in file 02, we've got static int var is equal to 100. So again, var always exists, static data, but static in this context means that it is only accessible within that particular file. It is only visible within that particular file. And in line 4, whenever we access int a is equal to var, then the one that is in scope is the one that is declared to have internal scope within this particular file. So we take it from that particular version. Static keyword, this is where it comes into the one notion of no scope. You can also apply static keyword to variables defined within a block of code. So if I call a method, say my foo method, and I'm declaring an integer within that, I can actually make that a static integer. Now in terms of scope, the thing I declare is only visible within that method. It doesn't have a scope outside of that. By putting in the static though, it means that it always exists. And that variable will exist across method calls. So when I call the function the first time, the second time, the third time, whatever that local variable is, it's going to keep that value from one call to the next. It is somewhat of a niche feature. Now, having gone through the notions of scope, of linkage, of static, of external, of global, of this and that, you might be thinking C++ is a tad confusing, it's maybe a bit messy in terms of offering all of these different options and doesn't necessarily sit together in a particularly clean way. If you think this, I would agree with you, you'd be right. More modern programming languages, Java, C#, things like that, they handle scope in a much cleaner manner. And in part what we're seeing here for C++ has been a little bit of the evolution of the language. But important takeaway thing from this here is that for the data, even if it may not be apparent or obviously visible within the language, where it is stored, how long it exists for, how broadly accessible it is in terms of the scope, these are all important characteristics of the data that we create. And they are things that we do make decisions about in terms of our design of our programs. Side to this here, for C++11, actually they sort of recommending using namespaces as a way of controlling access to data, and we'll have a look at those when we get onto classes. So that covers in static data, data that always exists. So we've had a look at automatic variables, we've had a look at static variables. The last thing we want to have a look at is dynamic variables. So these are things where the programmer is allocating and creating new memory. And this is where the new and the delete keywords come in. So anytime you use new, and this is in for Java as well, you are creating or dynamically allocating a new piece of whatever it is, reserving some memory for storing it. Any variables that we create this way, they get to be stored on the heap. So anything allocated using new automatically gets to be put onto the heap. The idea behind new is that you use new when you want to create something that's going to stay about for a while. It's not going to be sort of created and then immediately discarded. So the The operations around the new are a little bit more sophisticated. There's a fairly complex algorithm behind how we allocate new memory and how we manage the memory that we have available on the heap. We need this because when we're deleting or freeing up, say, objects we've created, we can potentially freeing up bits of our heap. It may not be at the end, it could be a bit in the middle of the heap. So you get into whole memory management setup about, well, do you let your algorithm have holes in the heap? Do you try to rearrange the heap to keep it all together? There's a whole bunch of different things that go on there. Important things to remember here then, so use new, it appears in the heap. There's a management process that happens in the background by way of actually looking after and controlling that particular allocation. So it isn't free. It does actually take, or can take a reasonable amount of time to manage this. For the delete keyword, this is something that managed languages like Java and C# don't have. In managed languages, the allocation and deallocation of objects are something that are managed for you. Okay, so we still say we want something created, but then actually deleting and freeing up that is something that is managed by whatever virtual machine you're running on. C++ doesn't have that, or C++98 doesn't really have that. There are some techniques in C++11 you can effectively get that out. So in C++, whenever you allocate something, it's also your responsibility as the programmer to delete it. And this is where the delete keyword comes in. Effectively, it says free up, release the memory that you were using to hold the whatever it is, the array or the class instance. Because the programmer has to remember to free it up, sometimes, most times, yes, you'll remember to do that. Sometimes you might forget, or there may be some reason where there's a flow through the program which doesn't free up some piece of data. If you get into any situation, you can see an example here, foo method, line 3, where we're allocating an array of 10 ints, so 40 bytes of memory. We process the data and then we leave the method, and we forgot to use the delete keyword to free up the data. In that particular case, that memory is allocated. It still remains allocated and is always going to be allocated for the remainder of that particular program. But we've lost our way of getting access to it. So this is actually a memory leak. And every single time we call foo, we're reserving 40 bytes, which we're never going to get back. And our heap is going to be getting bigger and bigger in size. And over a sufficient period of time, if we call foo sufficiently quickly, we're going to use all of our available heap. It's going to run into the stack, and we're going to have a out-of-memory exception. So one of the big benefits of managed languages is that you don't have that particular problem, generally speaking, that they will keep the heap in good working order. But in C++, part of the challenge then falls to the programmer to make sure that he or she manages that process. We're going to have a look when we get onto pointers, also about some other aspects of how we free or can free data up. So takeaways in this is really the same ones as the last memory look at on it. We do and we will want to understand how the data that we define gets to be stored within memory. It'll be stored in the heap, it'll be stored in the stack. If you want to get fancy, we can actually manipulate this in fairly nice ways, and a lot of the more sophisticated C++ programming techniques will get down to the level of manipulating data and jumping about memory, as you can potentially do things quite an efficient manner at that particular level. But we'll see that in some of the later talks.